So welcome everybody, but before I welcome everybody to what will be the 32nd Ockham lecture, I want to take this opportunity to make an important announcement, which is appropriate since this is as large a gathering of Merton physics community as we could realistically muster. So it transpired this year that there is an organization in the world called the Physics League across numerous countries for kick-ass students. Acronym PLANKS. And that is a theoretical physics competition worldwide, where teams from universities across the world gather together and solve physics problems as sport. So now in February there was a joint United Kingdom-Ireland final of this competition, leading up to the upcoming world contest, which I think will be in London in May, assuming the world still exists by then. In that competition, as you might expect, the Oxford physics students won, which is natural. Indeed, any other outcome would have been entirely scandalous. Now they have these teams that compete in this are entirely self-organized, and they have names. So Oxford won and beat Cambridge and the Imperial into second and third place, respectively, as you might expect. So the Imperial College team was called the World Sheet. I apologize with the Russian accent, you sometimes want to make sure that you get the vowels. The Cambridge team was called the Conserved Currents, suggesting, I suppose, that what's there is there and not much comes in, what comes out. But the Oxford team had a very laconic name. It was called Merton. And its members were Richard Chatterjee, Ray Mahmood, Oscar Mata, and Ross McDowell. And it won. So I suggest we congratulate them. Get up. With this fine achievement, you wouldn't have expected any other college to do any better than us, and so Merton and Oxford physics are now synonymous. With which, congratulations. So, and now we move on to another one of these iconic Merton physics events, the 32nd Ockham lecture, and I will hand over to Professor Arthur Eckert, who will introduce the speaker.
Well, thank you, Alex. And I have to say it's a common way to say it's my great pleasure to introduce, but actually it is my great pleasure to introduce Chiara Marletto, because she was one of my very unusual PhD students, I have to say. So I met her in 2010. If my memory serves me right, and she came to Oxford, and Chiara did her undergraduate studies in Torino, in Politecnico di Torino, where she was working on simulation solitons in DNA-like structures, so it was a rather applied topic. And so, and it started, a fascinating journey with Chiara, because somehow, right from the beginning, it was quite clear that Chiara had an appetite to do some interesting and sort of even wacky kind of physics. And so we did some more conventional things together, like state transfer in chains of spins and the like. But then Chiara ventured into something that I find extremely fascinating, namely of this sort of a twilight zone where physics meets computer science, meets universality of computation, meets biology, and so on and so forth. So I'm not going to steal her show, of course, because she's going to talk about it. But all I wanted to say is that I don't know how much Chiara learned from me, but I think I learned a lot from her because of her broad interest. So it's not only, we talk not only about physics, but quite often our discussion ventured into issues related to social sciences, literature, poetry even. And I was also a little bit amused by the title of the talk, The Physics of Can and Can't. So I thought that Chiara spent some time in, as you can see, one of her affiliations is Center for Quantum Technologies at the National University of Singapore. And there in Singapore, there's people, well, basically people speak English, but there's also a very peculiar variation of English, which is called Singlish, Singaporean English, where, and there's a very peculiar use of can. For example, in Singlish, you can say, for example, tomorrow can, which means can you make it, can we meet tomorrow? To which you can say, well, tomorrow also can, which means yes, I can make it tomorrow. But the most, I think, beautiful example of Singlish was when someone told me, you know, cannot also can. And I thought, oh, that's good, which means it's okay to say no. In Singaporean English, so cannot also can. So I think that, you know, this title has a lot to do with Singaporean English, but it's also, I understand, a wonderful introduction to Constructor-theory, which is something that Chiara has been working on her own, but it started in collaboration with David Dodge. So without any further ado, Chiara, the floor is yours, and we want to learn a little bit more about the constructor theory.
Okay, thank you. I think the mic is working. Well, thank you, Arthur, for this introduction. This was very, very nice. And also, thank you for being here. As I said, I mean, it's very nice to be here as, because I was a student, and you know, it's kind of very nice to see lots of friendly faces that remind me of that time. And just on the note of what Arthur said, I think one thing I've learned during my PhD with Arthur is that what is not forbidden is actually possible. And this will be one of the themes running through this talk. And in fact, it's a bit funny that this is going to be an Ockham lecture, because nearly half of what I'm going to say today is something that at first sight you would like to remove if you were to apply Occam's razor. So it's the kind of stuff that looks like it's accessory, not needed to explain experimental evidence, and therefore completely uninteresting for physics. And what I'm going to try to persuade you of is that actually this stuff is very useful. And by pursuing it and trying to understand it, you might actually accidentally, more or less accidentally, stumble upon something that will lead to new ways of looking for experimental evidence. And I think this is not an unfamiliar story to most of you, because I think this is what we always do in physics, ultimately. So I'll start with, forgetting about Occam's razor for a while, I'll start with a problem. A problem which is exactly in the field that I've been working in, which is quantum information. And the problem is that if you consider quantum computing, one way of looking at it is that it's an unfinished revolution. It's a revolution because it was a thing that taught us how something that looks pertaining to the realm of macroscopic emergent things, such as computers, can actually tell us something very deep about the structure of a fundamental theory like quantum theory. And it's unfinished because if you consider the way in which we proceed in proving things in quantum information, at least from the theoretical side, which is my own side, what we do is deeply relying on the theoretical structure of quantum theory. So we use the dynamical equations, we use notions like Hilbert spaces and other formal entities that are deeply entrenched in the quantum formalism. And yet we're talking about something that has to do with information. And information, as we know, is something that transcends most of the details of physical systems. So one question, one problem is it possible to imagine a further generalization of quantum information where we leave behind this formal structure and we retain the quantum information elements? What would that even mean? We don't know. We would have to develop new formal tools, new conceptual tools to address this problem. So that's problem one. Then we've got another problem. When we talk about the universal quantum computer, well, unlike what the name suggests, this is not the most universal machine that one can think of. And this was already known to von Neumann. So a universal computer is a computer which can be programmed to perform any computation which is physically allowed. But there are tasks, construction tasks, that are not computations. And the most important one, which von Neumann pointed out already, is the task of creating a new instance of itself. So a universal quantum computer can be programmed to do all sorts of computations, but if you wanted to program it to reproduce, to recreate a replica of itself, well, there's no space in the Turing machine kind of paradigm to even phrase that kind of program. And yet this is a physical process, because of course we know it happens in reality, in biology, with cells. This is something that in interesting discussions I had with Alex here, about exactly this issue of having a quantum machine that can self-reproduce. I think Alex suggested this weak name of replicant, and this is one of the interesting things that I've learned from Alex, that you should always find a nice way of naming stuff that you're conjecturing about. And I'll come back to that later. So, this is why von Neumann thought of the universal constructor. Now, it may not look like that. We don't have one yet. But this is the coolest thing I found on the internet, and that's what amused you. So, universal constructor generalizes the universal computer to a machine that can perform any transformation that's physically allowed, including self-replication. And again, is it possible, this is the second problem, to generalize the quantum theory of information to create a theory of these kinds of machines? So a theory that tells us how we can compose them. What's the rule that governs the programming process of such machines? And how are these machines related to things like artificial intelligent machines and so on? And now I want to consider another problem, which doesn't quite come from the field of quantum information, but it's something that's more broadly present in theoretical physics. So if you think of the guesses that we've had about the universe so far, the really good ones, possibly these four come to mind. And they look very different in the sense that they describe very different kinds of physical realities. For example, one is quantum, the other one is classical, there are waves, particles, etc. But one thing they all have in common is that they describe reality through dynamical laws, so descriptions of how objects move in space and time, and initial, or more precisely, boundary conditions for those laws. And this is a very successful, powerful way of describing stuff. And as you can see, the kind of objects I mentioned earlier, constructors, computers, and so on, don't really have space in this kind of description. as fundamental entities, because they're just described by some dynamical motion taking place involving a number of atoms, and therefore they're not so crucial in this view. However, there are other ways of formulating laws of physics. Principles. And here we have 3 examples, 2 less controversial than the third. So the first one on your left is the conservation of energy. So the conservation of energy says that it's impossible to build a perpetual motion machine of the first kind, which turns something that has energy, that has no energy, into something that has energy. And the second one, of course, is the second law of thermodynamics. I didn't put any formulation there because there are so many possible formulations of the second law that already tells you something about there being problems in a way, because people can't exactly agree on one single formulation of the second law. And the third one is not really a law, it's a more conjectural statement which goes under the name computability of nature. I think this is what the way David Deutsch phrased it, is the conjecture that a universal quantum computer or a universal computer is actually possible, it can be built. And that thing you see there is a nice pictorial representation of what could have been the first universal computer, programmable computer. This is Babbage, and this is Ada Byron, or they were collaborators, and in the Victorian times, they came up with this amazing project for building a programmable computer. Unfortunately, they didn't manage because they ran out of funding, and something that happens, as we all know. So the thing I wanted to point out in this slide is that there is this other way of formulating laws. And if you think about it, these principles are not really formulated in terms of dynamics, in terms of laws of motion, unlike the former laws that I mentioned, but they are formulated in terms of possible and impossible physical transformations. And so this connects back to the problem I mentioned earlier. I said that it would be nice to have a way of, for example, formulating quantum information in a dynamics-independent way. And here we have an example of things that are formulated in a way that's independent of dynamics, because they're supposed to hold for dynamical laws we know now, but they should also constrain future laws that we don't yet know about. So, by putting together these 3 problems and these various observations, you may understand how this program of constructor theory comes about, and I think it's now time to introduce it. So, this is more or less the way in which the problem of this new approach to physics was proposed by David. So, the idea is that laws of physics can be expressed not in terms of dynamical laws, but they must be expressed in terms of constraints about what physical transformations are possible, what are impossible, and why. And then dynamical laws are derived from these statements. They are emergent consequences. And you see there is an interesting switch in the logic. And the hope is that by doing so, you will be able to incorporate more of physical reality than what we can currently incorporate. Now, the first question is, of course, where do you start if you throw away dynamical laws? Because they are a very powerful tool, and it sounds a bit crazy to say that you want to do, you want to sort of leave them on the side and try to derive them from other statements. So one way in which you can start is to consider other elements as fundamental. So not trajectories, but tasks. And so you can state constraints about tasks, which are sets of ordered pairs of input-output. And a task is impossible if there is a fundamental limitation to how well it can be performed in reality. So I'm saying that the task is impossible not if it's forbidden by the laws of physics, so we're not talking about trajectories being ruled out. We're talking about a transformation which cannot be performed to arbitrarily high accuracy, no matter what you do to your physical system, no matter how many resources you bring about and so on. You can think of the conservation law example to understand what that means, because when you say that energy is conserved, what you mean is that there is a fundamental limitation that says, to the accuracy, let's say, that you can achieve in realizing a perpetual motion machine. Likewise, in quantum theory, we say a universal quantum planner is impossible. We mean the same. We mean that it's not possible to bring a copying machine for any two quantum states to an accuracy which is arbitrarily high. And note these would be the fundamental statements, and then the dynamics and the initial conditions should be derived from these ones. Now, you might actually be a bit lost by now, I hope not too much, because there is no constructor inside here. We haven't mentioned constructors, and I think this is something that in countless discussions with David we complained about, because the name constructor theory is slightly misplaced. The theory should be called something else, because constructors are not quite the fundamental entities. The fundamental entities are tasks and statements about whether they are possible or impossible. Constructors are, if you like, objects that you can abstract away from the picture. And why is that? It's because whenever a task is possible, it means that there exists an entity, which we call constructor, that can bring about the transformation and crucially stays unchanged in its ability to do the transformation again. So in a way, it's a generalization of the concept of a catalyst or a cycle in thermodynamics or a computer. But we don't care exactly what exactly it is, because the statements that are fundamental are the statements about possible and impossible tasks, and which particular constructor can perform a possible task becomes irrelevant. Just like when you say this conservation of energy, you're not busy ruling out all the possible designs of perpetual motion machines of the first kind. You just say energy must be conserved, and what that means is specified by particular notions of energy that you have in every specific physical theory. Okay, at this point, I guess, one doubt that might be emerging in your minds is, are you actually talking about shortcut physics? So this is some terminology which I've learned from Harvey Brown, I think, who is a philosopher that I've had many discussions with. So here an example of a shortcut physics law. So the law says, this comes from an interesting Monty Python sketch. So all brontosauruses are thin at one end, much thicker in the middle, and then thin again at the far end. And now, of course, there's a regularity in nature, we could say, because there's a law about dinosaurs. But unfortunately, it's not so fundamental. And I'm sure you're hoping that constructor theory is not a collection of statements of this kind. And the rest of the talk will be me explaining why it's not. And explaining why, in general, principles, such as the conservation of energy again, or the principle of locality, even though they look as very trivial statements sometimes, because they capture what we already see happening in reality, are very powerful. They are very powerful tools, because they are not dependent on dynamics. So they sometimes can be very useful when we don't know exactly which dynamical law to use. So at this stage, I would like you to just abandon this general picture, which is, let's say, the program of constructor theory, which may or may not work in the future, and focus on a particular problem for which these tools are useful, whether or not this big picture is going to pan out in the end. So the problem is a problem that I called the problem of hybrid systems, although, again, going back to naming things properly, hybrid systems have been used in the literature meant to kind of refer to all sorts of things. What I mean here is a very specific thing, and that's the following. You have a system which is this Q over there, which obeys the laws of quantum theory. And for those who are not quantum theorists, this just means it obeys a specific law of motion, which we know well. And then there's another system, M over there, which stands for mystery, mysterious. Something that, of which we know a few details, but we can't assume that it obeys quantum theory for sure, in fact any other dynamical law. And the question is, can we make statements about the composite system in a way that we can make predictions and then maybe make some experimental tests? Of course, there are ways of doing this just by approximating the behavior of M with some known dynamical law, but what I would like to do here is to use these principles of constructor theory to address the problem. And we'll see that this is extremely helpful in the case of a problem which cuts deep at the foundations of physics right now, which is the problem of merging the two fundamental pictures of reality we currently have. Quantum theory on one hand and general relativity on the other. Okay? So, to explain this problem more closely, I will need to make a detour in quantum physics. And I'll introduce a number of properties which are useful for our discussion. So, the first thing you probably encounter when you understand quantum theory and you study it in textbooks is this thing called Heisenberg uncertainty, which is slightly misnamed. And this is a nice thing that I think I learned in discussions with Arthur. So, you can take a photon as a typical quantum particle. And in quantum theory, you can say that a photon can be in a quantum superposition of two different locations, two different paths. And how do you create that? Well, looking here on the left, a photon goes into a beam splitter, which is a particular kind of instrument. And the photon is split into two different paths. And at this point, it's exactly in this state, which can be described in quantum notation at 0 plus 1. Which means, well, as we know, we can't quite say what it means. It's not that the photon is in both arms. It's not that the photon is either in 0 or 1. But one thing we can say is that the photon, when you check where it is at this stage, well, it's unpredictable where it is. So you sometimes, if you observe it, you will see in 0, in path 0, some other times in 1. But it's unpredictable to say which position it has. On the other hand, when it is in a superposition of this kind, there are other observables that are perfectly predictable and deterministically predictable, and that's the quantum feature about the photon. And we can see it on this side, on the right side here. This is an interferometer, and it consists really of doubling the first instrument here. So you've got one here, and then you've got two mirrors, and the photon recombines in the second such instrument. And very interestingly, at this stage, you always see the photon in one port. So the outcome at this stage is predictable, completely predictable, deterministic. And the reason is that you are actually measuring a different observable of the photon, not the path, but related, let's say, to its energy. And this is, of course, what Heisenberg uncertainty is all about, the fact that there are different properties of the quantum system which, when one of them is sharp, the other one isn't, and vice versa. Now, the other aspect of this duality is the possibility of entangling two particles, which is a chiefly quantum feature. And, well, this is one of the standard schemes that you can use to describe what happens when you entangle two particles. This is, for example, one photon and there's another one. And they are in a state, at this stage, which can be described as a state which has special types of correlations which are proper only to quantum systems. And what you need in order to follow the rest of the talk is just that in order to confirm that two particles are entangled in such way, you have to make measurements on each of them that involve at least two of these incompatible observables that I mentioned earlier. So here you see that it's very interesting that to confirm that something is in a quantum state, it's quantum entangled, you have to be able to operate on it through some quantum transformations, which allow you to measure these two incompatible observables, which only exist if the object is quantum. So this will be useful for later. Just bear that in mind. And entanglement is interesting because it can exist only because there are these incompatible observers. And it's also interesting because, well, it's useful to describe what happens when you observe a quantum particle. And of course, we're going here into the realm of science fiction. But if you take quantum theory seriously and you apply it to an observer here, perhaps on the hair you might recognize me over there. This observer is coming along and there's a photon here, and the observer is looking for the photon and wants to know where the photon is. Now, the way in which quantum theory operates is that if this observer obeys quantum theory, it will join the superposition. So it will become entangled with the photon, and so there'll be a branch in which the observer sees 0 and another branch in which the observer sees 1. And of course, I leave it at that because there's a question of what does that mean? Is it just one observer? Are there two observers? People have discussed and written a lot about this, but for the moment we just have to bear in mind that there is a conjecture that whenever there's a quantum particle in the universe and there's something that can couple to this quantum particle, it will become quantum itself and join the superposition or the entangled state. And there's no end in sight. I mean, this is the notorious bigness friend. I think you can imagine another fellow coming along and asking me whether I've observed a path on the photon on path 0 or on path 1. And this fellow also will, if he obeys quantum theory, join the merry entangled state. And here we go. So there are 3 elements here. And they are all consistent. So this guy that's coming along will never be inconsistent with me, because once he is interacting with this observer, he will ultimately be seeing exactly the outcome that the first observer saw, and so on. And you can continue like this ad infinitum. And I don't want to dwell here on what is the way of understanding this. The only thing to say is that you might recognize this as the nice pictorial representation of the quantum multiverse, which appears in Philip Pullman's books, which are nicely inspired by this scientific idea. Although he unfortunately gets some of the physics wrong, but probably that's because the story is just better like that. In the sense that you can jump from one universe to the other and people can talk to each other. And actually that's not true in quantum theory. Now, I promised I would tell you a problem. So all of these elements were just for you to understand what the problem is. And let me go back to it. So the problem is that this hypothesis, this idea that any object, that if there is some quantum superposition around in the universe, that there is something that interacts with it, this thing will also join the superposition and become quantum, so to speak, may not be true. And one reason why people think they may not be true is that there is a theory which describes one of the most fundamental interactions in nature, which is the gravitational interaction, which says that things are fundamentally classical. So if you consider Einstein's theory of general relativity, or in fact most theories of gravity we have at the moment, they are formulated in a way, other than quantum gravity, they are formulated in a way that they suggest that gravity is a fundamentally classical field or entity, however you want to call it. And this is a problem, of course, because objects which can be in superpositions have masses, and they have energies, and they can therefore interact with gravity. And the question is, how do we describe that? And this is a problem that all theoretical physics know about. And it's what led to an ongoing science friction. So this has been around since probably this time or even earlier, between a camp which says that gravity must be ultimately be quantum, and another camp which says that no, actually gravity is ultimately classical. And this is the reason why quantum theory is not universal, because ultimately if a mass is large enough, it's going to, so to speak, collapse the wave function and make it classical. And the reason why there's 1957 there in Chapel Hill conference is that at that conference, this science friction occurred in a very spectacular way. You can read the proceedings, they are really beautiful. Specifically, there is this exchange between Hermann Bondi and Richard Feynman. They were discussing exactly this issue. And to this day, the debate is still ongoing. And now we can recognize something familiar, possibly, from what I said earlier, that this case of having a quantum system interacting with one that is mysterious and we don't know whether it obeys quantum theory or not, is actually a general case, which includes the case where you have a superposed mass, a mass superposed across two locations, and the gravitational field. Of course, there are several candidate models to describe this. There are a number of models of quantum gravity. But alas, there is one problem with them, which is that, well, other than several mathematical challenging problems, that it's hard to test if you assume that M gravity obeys quantum theory in one of these quantum gravity models. Is hard to perform tests of these facts. So these models suggest that gravity might be quantum, but there is no practical way of testing whether they are right or not. And so this problem, which was pointed out by Feynman already at that time, in that conference, how does one actually test that the gravitational field joins the mass in a superposition? It's entangled with the mass when the mass is superposed across two locations, is a problem which is still unsolved. And the issue here is really, how do we confirm that the gravitational field has quantum features? And remember what I said earlier about confirming, let's say, that something is entangled with something else. In quantum theory, we know that to do that, we need to measure at least two incompatible observers of that object. The one that we want to show is actually entangled. And here, we don't know if those observers are even there, because we don't know if the gravity is quantum. Okay, so here is where these general principles may be useful. And so this is some kind of structure which you can describe in constructor theory, where objects which are not quantum systems are at least dot, objects which are not quantum but have some features that quantum systems have, so specifically they have these incompatible observables, can be described as a special case of systems that I call information media, which are systems that can carry information and obey, let's say, some classical laws. So you can construct this very nice exact structure where the quantum systems are now a special case of a more general set of systems which obey certain principles. And these principles are information theoretic, and they are exact, and they are scale independent. So maybe we can use them here. Maybe we can use them to make these predictions which we were looking for. And actually, that's what turns out to be the case, which is what I'm going to tell you about now. So you start with some assumptions which are formulated in constructor-theoretic ways, and they are principles that, just like the principles I mentioned earlier. One is the principle of locality, of course, which we all have an intuitive feeling about. And the other one is this thing called the interoperability of information, which, if you want to have an intuitive explanation of, you can think of a principle that says that when you take two systems that can independently contain, let's say, each one bit of information, and you put them together, you expect that the composite system can still operate as an information medium, so it can still be used jointly as storage of information and as a thing that you can use to process information. Of course, these are just words. There is a mathematical formulation for this, but I think this is the intuitive feeling of what the principle says. And note that this is not trivial, because it's something that we all assume when we imagine information processing occurring in a computer, because we know that a bit can be instantiated in all sorts of different substrates. But the fact that if you take any such substrate, like a specific kind of a transistor, and you consider another kind of substrate that can also instantiate a bit, which could be, for instance, a photon, and you consider the joint system, the fact that there must be a way of using both as a 2-bit system is a non-trivial aspect of the laws of physics as they are. And the principle actually expresses it. And now, this is what happens when you consider the two principles together. And you apply it to this problem that I mentioned earlier. You can prove a general fact, a general theorem, which is useful to the problem that I was describing. So, imagine you have a system made of 3 objects. So, you've got 2 quantum systems. So, each of them behaves like the photon or the mass, which can be put into a superposition of different locations. And then you've got this system M, which just obeys the 2 principles that I mentioned earlier, and we can't assume anything more than that. And you consider the joint system, you can prove a nice theorem which says that if M can entangle these two quantum systems, then M must have some non-classical feature. It must have specifically these 2 incompatible observables which are proper of the super-information media that I defined earlier, which was this generalization of quantum systems. And the interesting thing about this is that you can show this without committing to a specific dynamical model. So it's a bit like these derivations of the redshift, for example, from first principles. You can derive the qualitative version of the redshift from just assuming it's something that Bondi did at some point, from just assuming the conservation energy and the equivalence between mass and energy. And of course you will have a qualitative result, but it's exciting because you can say something about the system that you wouldn't otherwise be able to describe just with dynamical laws. And it's interesting because to test that M is quantum, or has these non-classical features, you only need to probe it with 2 quantum objects, and therefore all the measurements are done on these 2 quantum objects. So you never actually directly measure features of M, you just measure the probes. And this is what really excited, I think, Vlatko and I when we thought of this, because it was an interesting instance of this powerful logic that principles in physics provide us with. And so now you could say exactly this application to the problem of testing whether gravity has some quantum features. And there is an interest from experimentalists to try to perform this experiment. And this would be very interesting because it wouldn't allow to confirm any specific model of quantum gravity, or it would not give us very useful information if, for example, the entanglement can be achieved. But if it can be achieved, then it's ruling out all these classical pictures of gravity which we have been using so far. And that's a useful element to add into this debate between the camp that says that quantum theory is universal and the camp that says that, on the other hand, it is not, and ultimately there is part of the universe which is classical. So, of course, one question is, how feasible is this? Now, the answer is, I don't know exactly, because this is something that we are actually discussing with lots of experimentalists who are very interested in trying to realize this. But a rough indication of whether we are maybe closer to this than to other experiments which could test quantum effects in gravity is this line, where, of course, the electron is not represented. Here is Schrödinger's cat, which, of course, gives us some kind of sense of what a really macroscopic superposition would be. And here is Planck's mass, which is the mass at which most physicists would expect quantum effects in gravity to become important. Here in red is circled the mass that one would need in order to extract some useful entanglement from these masses and be able to infer something about the gravitational field which mediated the interaction. Interestingly enough, is more or less overlapping with the mass of a human cell. And here we have viruses, which of course we're all talking about a lot now. So it's quite a large virus, I would say. And here are buckyballs, which were in the past main actors of this brilliant set of matter wave interferometry experiments that were made involving these quite large molecules. And I think the limitation for microscopic superposition is somewhere around here. So in a way, we're not that far. And now the question is, people are trying to actually see how to realize this. Of course, this depends on the technology that we're using and so on. But what I was interested in today was just a matter of principle, something that I think is interesting for theoretical physicists and for experimental physicists, and maybe philosophers too, that by pursuing some problems which are not quite in the data as they are, because both quantum theory and GR are very well confirmed experimentally so far. By pursuing problems that are just present in our theoretical ways of describing the world, you might actually stumble upon an experimental unexpected scheme that you can use in order to solve some of these open problems. And so the kind of oral comment you might make at this point is going back to Occam's razor. Do we really need Occam's razor? Is it not just enough to consider problems, open problems, and throw away theories that are problematic and keep those that are not? And when they become problematic, we revise them. I think most of us would agree that this is the case. And perhaps even Ockham would agree, I would say. Maybe the way in which Occam's razor is currently portrayed in the literature is not quite what Ockham really meant. And so, last thought before ending is, what happens if you actually apply the razor to itself? Do we really need Occam's razor to conjecture things? Or do we really need it to explain the scientific method or not? And because I'm just a simple-minded physicist, I think I'll leave this to people who are more philosophically minded. And I'll stop here. So thank you for your attention.
Thank you, Chiara, for this introduction. And now we have plenty of time for you guys to elicit further insights into what happens if you take Occam razor to itself, or indeed if you take it to Schrödinger's cat. Questions? Please.
So, when you said that you'd be looking at entangling two masses the size of a cell, like obviously there's a lot of potential complexity involved in that. What type of experimental setups are people looking at to sort of mitigate the complexity within the two masses to be able to show these effects?
So I think currently there isn't an actual proposal for a specific experiment. I think there are a number of theoretical proposals which have to go through a feasibility study. But there are a number of systems which you can think could be useful. One of them is there are some nanomechanical oscillators which have roughly the masses that are needed and can be controlled in a way that could be relevant for making the measurements that you need to do. Others would be masses that are, so you can try to push the current benchmark for the matter wave interferometry kind of experiments, as I said in this previous slide. So I think there's a group in Vienna that is led by Marcus Arndt, who is trying currently to push further and further this limitation to macroscopic superpositions of large molecules. I think the latest was that he was trying to superpose a virus. And so the hope is that there will be a way of pushing this limit further. But the thing that I think is interesting and suggests that this might be a better way of approaching the problem than others is that the emphasis is that you don't have to directly detect quantum features of the field, but you can rely on this indirect evidence that comes through the entangled particles. Of course, it's very challenging to create that entanglement, but so in a way, you're pushing one challenge into a different challenge. But somehow we're more confident maybe on this one because we have a lot of technological progress already happened. So we're hoping this will be more approachable as a problem.
Please.
Yeah.
Why does the for the test? Why does the mass have to be so big?
Well, it has to be so big because that's a nice question. Because when you express the entanglement as a function of the phase that is created between the two masses, there is this gravitational coupling constant, which unfortunately conspires against you. So I think this actually is what makes most experiments about these effects very challenging. And this is also why, while it is quite okay to detect a photon, the equivalent kind of particle, which would be a gravity, is very hard to detect, in fact impossible. So I think the reason why the mass has to be big is because of the fact that you're fighting against this smallness of the gravitational coupling constant. But as I said, is less large than Planck's mass, which is the one that one would expect to be irrelevant to these kind of effects. So there was a kind of glimmer of hope in this result.
And whereabouts did you get Planck's mass from?
Well, Planck's mass well, the way you get Planck's mass is mostly this dimensional argument, which I find sometimes maybe not so satisfactory, I would say. There are some arguments to indicate that if you take a specific quantum gravity model, that is the mass which is relevant for effects that would allow you to detect gravitons, emissions of gravitons. But I think the arguments by which you derive these things are possibly not as watertight as one would want. So in a way, they're just somehow indications, as I said.
So, again, I know nothing about constructor theory, but it's very, very interesting, especially at the beginning when you're talking about conservation laws. So is one of the main goals of constructor theory to derive a kind of a new set of conservation laws that we wouldn't be able to get from the way that we do it now, where you get dynamics and you apply Multiverse theory and you get some kind of conserved quantity? Are you saying that there are, because once you have a conservation law, you can get dynamics from it. Are you saying that there are new things that maybe you'll be able to uncover that?
Yes, I think that's a nice question. So for example, this interoperability of information, this is some work I'm doing with a different student here, receiving that, by the way. So the interesting fact is that when you formulate the interoperability of information as a mathematical constraint, you see that this is added some kind of symmetry on top of a certain dynamics. And so in a way, it's an open question whether you can associate to that some conserved quantity. But there is a sense in which the presence of this constraint suggests that there is a sort of symmetry in the system which allows you to make some general statements about two different systems which may obey different dynamics, so long as both dynamics comply to this constraint. So in a way, yes, it's a generalization. So hopefully, if the problem pans out, it should generalize this logic that you mentioned with Nusselt's theorem, but in a way that doesn't maybe rely on Lagrangian mechanics and things that are as specific as that. So it should be possibly even more general.
Do you expect to be able to get like equations of motion from these, or is it something more subtle?
this should provide some constraints on equation of motions, and as I said, I'm kind of agnostic on whether this will pin down one equation of motion or not. What I'm interested in here is to use these general constraints, once you formulate them mathematically, to make predictions where we can't yet assume a specific dynamics. So in a way, it's a bit like the way I'm thinking of these principles is similar to guidelines, let's say, that you can apply when you don't know yet which dynamics you can choose. And then if the problem pans out as expected overall, then maybe there'll be a way of using these statements as your primitive elements and then understanding dynamics as derivative. But this is really far in the future, and I really don't know whether it will be like that or not.
Does constructor theory provide some resolution for things like the measurement problem or black confirmation paradox or things like this? I don't think there is a measurement problem. But let's say if you think there is one, it's possible that by using these general principles about how objects that can process information like measurement devices operate could be useful to understand the problem better and then realize that maybe there isn't a problem. So on that one, it would be nice maybe to discuss a bit more, and then I can say why I don't think there's a problem. But about the black hole information paradox, well, okay, I'm afraid I also don't think, I'm not sure if I think there is a paradox, so that's actually an open where people, have all sorts of views about that. But maybe one thing for which this could be useful is that a black hole is one of these hybrid objects where the kind of dynamics that you can apply may or may not be so well defined, especially in certain regimes. So it's possible that some principles from this theory could be applicable in that area as well. So yes, the answer is going to be yes to both questions. What got me thinking was that there's some principle of information conservation.
Yes.
So this is a conservation law, much like energy conservation. And would this be built into some constructor theory?
Yes, right. So I think the interesting thing would be that you could talk about information carrying degrees of freedom without having to commit to a specific formal theory to describe your black hole or object in question. So for instance, you can talk about distinguishable degrees of freedom without having to represent them as orthogonal states, let's say. And this could be useful depending on the particular problem you want to solve. But yeah, I think these areas that you're mentioning, especially the black hole kind of area, are the kinds of areas where these principles might be useful. Because maybe our dynamical laws are not as well established in those domains.
Simon, I think you have a question.
Yes, this is a fascinating talk, but I wonder, what is special about gravity here? Could you take just a classical system, interact with two quantum systems, and deduce something comparable?
Yes. Yes, actually, this is a good point. So the nice thing about this result is that it is general. So it so happens that it can be applied to the gravity issue, but this could work with any system of which you can't assume the full quantum theory laws. In fact, there are cases where, for example, you have, I think this is something that also Glasgow was working on a lot at some point, where you have this, in quantum biology, for example, you have these systems that are interacting with light, this photosynthetic material, and you're trying to show that they are actually interacting with it in a way that involves at least some quantum features. And of course we know that the atoms of inside bacterium obey quantum theory, but through this mechanism, if you could make appropriate measurements on the field, let's say, you could infer that the relevant degrees of freedom for the energy processing are actually operating in some non-classical domain. So I think, yeah, I think that's a good point.
Just to follow up a bit, Niels Bohr famously claimed that macroscopic systems have to be classically describable, and by virtue of that was going to essentially avoid the measurement problem. And what I thought was most studies showed there was just no consistent coupling at all between the classical mechanical system and the quantum one. So there's sort of no-go theories like this. But have you circumvented those, or have you used them?
No, I think this is, again, a very interesting question. That these noble theorems are proven within, let's say, some underlying Hamiltonian dynamics. So they fix a model with certain dynamical features, and then they show that if you insist on describing a fully quantum system coupled to a classical system in that framework, you will find some inconsistency either with the conservation of energy or with other principles. But here, the coupling is in the form of requiring some transformations to be possible on the composite system. It doesn't require to fix the dynamics. So you just say, okay, I want this transformation from A to B to be possible on the overall system, and this corresponds to a certain kind of coupling. I don't have to specify which one it is. And then from that requirement and from locality, you derive a number of consequences. Which is why you pay the price of not having a fully quantitative result, because of course you need a dynamic model to have a quantitative result, or at least, let's say, that's what we think. But on the other hand, you can get a nice, interesting qualitative result. So I think this is not in contradiction with those other things that you mentioned. They coexist. It's just that this is more general.
So the locality you just mentioned. So the theory of gravity is, let's say, a global theory. So local is just Minkowski. Are you saying something for the terminology of locality?
Yes, maybe I should have said. So I think by locality we mean a property which is perhaps better known as no signaling, which of course is satisfied by all theories of interactions that we currently know. And also about your point in terms of the global nature of gravity, let's say. This experiment is happening on scales where the general relativistic effects are not relevant. So it's a very interesting regime in a way, because it can be described as an almost flat manifold. So it's completely local in that sense. But it still probes some non-classical features of the gravitational field. So it's not a regime where GR is important, but it's a regime where these quantum effects already bring some differences from a completely classical model, which is also maybe why it's perhaps more accessible than other proposals. But I think it's a very good point. I think locality, unfortunately, is a very loaded term. It could mean all sorts of things, but in this case it just means if I do something over here, stuff over there can't be changed in a way that can be detected, unless there is some signal that travels from here to there. Yeah. There is some.
Yeah. So you talked about not needing to describe some dynamics, but at the start of the talk, you talked about also not needing sort of formal apparatus like Hilbert spaces.
Yes.
Or at least you mentioned Hilbert spaces. And then now think about the composite system of the quantum system and this mystery system. How do you talk about the state of the composite system without mentioning a Hilbert space or something like this?
So you can go back to some very primitive or fundamental, depending how you look at it, mathematical tools, which is basically set theory. And you can say that you have a theory which describes each of the systems with some state. Doesn't matter what, it's just a descriptor of each of these systems. And then you consider sets of such descriptors, which are attributes, so they correspond to maybe what in quantum theory we would call subspaces. And then you can consider all the pairs of these things. And then you can make statements about those. And so in a way you need maybe a topology to be defined to make certain statements. For other statements you need a distance, a notion of a metric to be given. But you don't have to specify which particular metric it is or which particular topology. So long as there is one, you can then prove your results in full generality. And of course, Hilbert spaces are a special case of this stuff. And I think, as I said, Marletto here, who's working on this stuff, is can also maybe discuss this later.
Maybe while you're catching your breath thinking about more questions, right, I could ask a question. This will necessarily lower the intellectual level of the debate, but it's inevitable since they're not raising their hands. So these constructors that you said perhaps shouldn't play quite such a prominent role in the name of the theory, and yet do. So one of the requirements was that they have to survive constructing.
Yes.
Right? So you said they had to do the transformation and then survive. Why do they have to survive? Why can't you have kamikaze constructors?
So actually, this is a very, very deep question.
Oh, thank you.
I think touching on a number of, yeah, okay. So, well, so one thing is that when you look at some partition into subsystems of the universe, right? So you say, okay, this is a system, there's another system, and I decide to partition my system like this. In thermodynamics, for instance, you say, okay, this is my system, that's the environment. Then these partitions are usually arbitrary in the sense that there is nothing forbidding you from switching and thinking that your system is the environment and the environment is the system. Here, we're trying to say that constructors are a special kind of environment which has the feature of being necessary for a transformation to occur, but on top of it, they also have to have this property that they go back to the original state once the transformation has occurred. And this is why they are not exchangeable for the system in question. So the stuff that gets transformed, and the stuff that, so to speak, is necessary and sufficient for the transformation and stays unchanged is a constructor. So it's a characteristic property that allows you to talk about a constructor in a sort of objective way, which is not an arbitrary, it's not just based on some arbitrary distinction between substrates and constructors. And so there's one aspect of your question. Why is it that we are looking for constructors, or in fact for possible tasks? It's because that's one thing that gives us a handle on talking about this partition into subsystems, which is not just completely arbitrary. And this also gives you a handle on cause or enabling things, which obviously has been, this terminology of causes is probably not so good in physics, but if you think of the terminology of enabling something, again, if you've got two systems interacting with each other, you can say that one enables the transformation in the other or vice versa. And again, there's no a priori reason why one shouldn't be the other. But in the case of a constructor enabling a transformation of something else, you can say that actually it's the constructor and not the something else to enable the thing, because the constructor has this property of remaining unchanged, this invariant property.
So if he dies, he was part of the system in the first place.
Yes, so it's not a good constructor. I mean, it's just not going to be able to repeat the transformation again. So I mean, if you put a can of Coke in the fridge, you're hoping that you'll be able to repeat this thing a number of times before the fridge, stops working. And so,
but if the fridge stops working, the Coke is still cold.
Yes, that's true. But then you need another fridge. Unless you actually, of course, if you go into a self-destructive mode and then you're going to, so I don't want to go down that sort of line. But this is interesting what you say, because I think so von Neumann, or at least, I'm not quite sure whether this was von Neumann or someone else who was thinking about what von Neumann said, was also saying that a universal constructor should be a universal destructor, something that could destruct anything that you could think of being there in the universe. And there is a bit of a paradoxical fact, which is this, that suppose you wanted this machine to be programmable to extract, let's say, any sequence of DNA that you can name. So you load the machine with a sequence of DNA, and you require the machine to go around in the universe and destroy each one of the sequences of DNAs that are actually the same as the one in the program. And then you would say, okay, this is a universal destructor because I can program it with any sequence,
and it will be able to do the task properly. Well, unfortunately, to be a proper destructor, at the end of the task, it should also destroy the sequence that you programmed it with. In fact, it should destroy any copy of the sequence that is present in the universe. But doing so will prevent it from being able to perform the task again. So you see that there is a... So it's not so true that a universal constructor is also a universal destructor, and this is actually why the concept of constructor is important, because it allows you to distinguish between all these cases. Just in case, if you want to destruct something, just don't think you can do it again.
There are opportunities clearly here for defense funding. I think we are the philosophical point.
Well, actually, no, I'm fascinated by your main result, as it were, or what for me is this wonderful result you've got, that you can't couple to this classical system and produce entanglement. But so, just to simplify the simple case, take a superposition. Is it possible to couple to a classical system such that the superposition one-term is destroyed?
Sorry, say it just...
Is it possible to couple to a classical system, to a superposition, maybe macroscopic
yes.
terms? Is it possible to couple to a classical system such that one is destroyed? I would imagine that a corollary of what you proved is that you can't do that. Is that correct?
Well, yes, so the point is that the superposition is possibly
it's a
what...
stable system now, in the superposition states. Can it couple to a classical system?
Yes, it can, and then one of a number of things can happen. But the point that we're making is that if you can evolve that initial superposition, which possibly describes two non-entangled subsystems, into one that describes a system where the two objects are entangled. And you did this by this local interaction with the mediator, which that we said is initially supposed just to have some classical information-theoretic features. Then you must infer that this system that mediated entanglement has to have this non-classicality feature. Doesn't mean that it's fully quantum, so it doesn't mean that it obeys Schrödinger's equation fully. But it has to have this feature of not of being able to hold two observables that are not well, they are incompatible. They can be simultaneously measured by the same object to arbitrarily high accuracy. So it's a lesser property than a full quantum structure, but it's something that can be completely classical. Sorry, I just want to add one thing. Of course, you have to be able to sustain the superposition for. So this doesn't mean that all classical systems coupling to any quantum system will kind of behave coherently. That's not what the result says. It just says if you happen to be able to do to kind of create an interaction in the lab which allows you to do this coherent evolution overall, then the subsystem which mediated the interaction must have these features. Of course, it's very challenging to be able to do that, but in principle, one could.
So maybe for those people here who are still to take quantum mechanics in their careers, do you think you could give them an example of an irredeemably classical system?
Well, maybe there isn't one.
Aha.
Are you asking me for a textbook opinion or because once I said something...
Something for which this result will not work.
Oh well...
Or so, for which it will prove that this is not... I think this is interesting because I think in the sort of sub-circle that I keep talking to, which includes Arthur, Blatko, David, and the students who are coming here to listen to this lecture and a few other... So is that a classical system? Or
that is a classical system, but no, it's quantum. That's a quantum system. So that's so for those, whenever we have discussions, we are kind of assuming that everything in the universe is quantum, and it's just a question of kind of persuading this system with enough persuasive means to become quantum, to behave quantumly in a kind of open way. But of course, I mean, there are views that oppose this, and so there is a view, for example, that whenever a sufficiently macroscopic object interacts with the superposition will collapse, and
Of course, the prominent sort of proponent of this idea is Roger Penrose, who has this view about the state reduction, which might be actually due to some self-interaction due to in the quantum superposition itself. There are other forms of collapse. So in any way, these kind of views would like to modify the laws of motion in quantum theory to make them so that somehow the classical appearance that we have is the fundamental thing, and the quantum world only exists in a sort of restricted domain. And what you've seen here is possibly a dialogue between these two parts, because of course those who suggest that collapse should occur at these scales are predicting that we won't see entanglement, and those who on the other hand think that quantum effects are always there, we just have to persuade the matter to behave like that, who predict will kind of say, okay, of course, this is obvious, we are going to see entanglement. And but if you really want to think of classical objects, you think of yourself, like, you know, an observer, observing stuff. Sometimes people, there was Wigner who was obsessed with the idea that living systems could somehow evade the laws of quantum theory. He even wrote a paper about it where he said that a self-reproducing entity somehow violated unitarity. It's kind of an interesting paper. He was wrong, but I think there are some strong intuitions behind this, and I think there is actually still a very strong heated debate about this stuff. And this is possibly one, you know, could help, let's say, if this experiment was done, because at least we can say, okay, gravity, at least at these scales, can behave quantum mechanically.
So the reason you focused on gravity is that that is the last nail to
drive
yes. into the coffin of classicality.
Oh yeah, of course. The other one being that we have to superpose. I mean, there is this David's experiment, of course, to superpose a human, or actually not really a human being, but let's say an artificial intelligent entity. And of course, that would be also an interesting experiment to perform. Could be very far in the future, but it's not really forbidden by the laws of quantum theory. So, as I said, what's not forbidden is possible, and you just have to wait for it, or maybe work on it, depending on what your interests are.
So on that optimistic, or for those of us who are classical physicists, pessimistic note, let's thank Chiara again.